లేదండి. నేను సావరు. నేను మర్చిపోతాను ఈరోజు.
నేను Hello everyone, very good evening. So let us get started. Yesterday we have started our discussion on inferential statistics, and we have understood so what is the difference between the descriptive statistics and inferential statistics. And also we have discussed about the central limit theorem, right? So we discussed that what is uh, the concept of the central limit theorem. And then today we are going to discuss about the first inferential statistics, so that is confidence intervals. Right, so confidence intervals we are going to understand with an example here. Okay, we'll come back to this little later. Yeah, so just take a few seconds, read this example. Okay, so we'll discuss and we'll solve this problem using this confidence intervals. Yeah, please go through this example, and we will have a discussion on this. So after a few seconds. All right. So let us discuss about this example. A university with 100,000 alumni is thinking to give a new affinity credit card to its alumni. Yeah, so there is a university, they wanted to give a new affinity credit card to their past students. Okay. So to run this project, that means they print the credit card, they execute all these things, right? So to run this project, they need some money also, right? So the profitability of this project depends on average the outstanding balance maintained by the card holders. That means if the student takes this credit card, if they use more and more, then the usage would generate the money and they can run the project without any hiccups. So that means the profitability of this entire project depends on how the students are going to use this card. If they use more and more, so they can generate some profits. Otherwise, so this would be a loss-making project for the university. Now, so to test the waters, to understand how the usability of this card by the students, the university wanted to run a pilot study, a market research campaign. Okay, so the university has launched a market research campaign in which 140 alumni accepted the credit card in a pilot launch. That means, so they wanted to test on these 140 students, whether how the project would be going. And then, so they have collected the data, university has collected the data. So on this 140 alumni, so how they are using this credit card, so all these things. And they computed the descriptive statistics, the average balance maintained by these 1990 dollars by these students, and with a standard deviation of 2833. Now assume that the population standard deviation is 2500 from previous launches. Now the question here is, the university wanted some advice. So what can we say about the average balance that will be held after a full-fledged market launch? So this is the question that we need to answer. Okay, let me explain. So by taking the numbers, okay, the key terms here, what do we have? So we have the population data. Okay, 100,000. Yeah, 100,000 alumni. Now the university wanted to give a credit card to these all the students. Okay, but so to run this project, so they need to generate money from this project itself, right? And they wanted to know, so if they give to 100,000 students the credit card to these students, what would be the average balance, outstanding balance maintained by these 100,000 students? That is 1 lakh students. So how do we know that information? One way is give the credit card to all these students, okay, and wait for 1 or 2 months, get the details from each of the student. First student, what is the average across the 2 months? Let us say $1,000. Second student, let us say $1,500. So like that for all the 100,000 students, give it to the credit card, get the details how much they are using, the outstanding balance, then take the average. So that would be the population parameter, that is average outstanding balance maintained by these students. But is it possible without testing the waters, without testing how the things are going on? So can we jump into the full-fledged implementation of this project? Meaning, so can we go ahead and issue the credit card to these all the students? No, that is not advisable because we do not know whether so this project will run into losses. So who will bear those losses, right? So in order to understand, so how the students would react to this credit card, whether so these students are going to use the credit card or not. So that is what I want to test it. For that purpose, so we have launched a market study. Okay, so as part of that, we have sampled randomly. Okay, randomly we have sampled 140 students. So this is sample. 140 is a sample size. So these 140 students, so we have given the credit card and we waited for, let's say, 3 months. Then for each student, we have collected the average balance, outstanding balance maintained by each of these 140 students. So first student, let's say 2,000 is average outstanding balance. Second student, 1,500. Third student, 2,200. So like that for all 140 students, we have collected the data. Now the average of this, the 140 students, so came out to be $1,990. Okay, $1,990. And the standard deviation is 2833. Okay, this is X bar. So this is smallest. This is 2833. Okay, so these are the statistics have been generated. These are called as descriptive statistics because from the sample data we have generated, and that's where we can call them as descriptive statistics. All right. Okay. Now also they are asking us to assume the population standard deviation is 2,500. Right? So that is sigma 2,500. Fine. So these are the data that has been given to us. Then what is the question here? The question is, what can we say about the average balance that would be held after the full-fledged market launch? That means, so if I give credit card to all these students, 100,000 students, what would be the average outstanding balance? That is what I want to find out. That is the population parameter mu. So if I give credit card to all these 100,000 students, 1 lakh students, what would be the mu value? What is the average for these 100,000 students? That is a question here. So is it clear to you guys, everyone? Is the question clear? All right. Now coming to the answer. So in order to answer this question, already we have taken the sample here. Okay, and the sample, the mean is 1990. So can't we say that is 1990 itself would be the average outstanding balance when you roll out these projects to project to all these 100,000 students? So can't I say that, hey, this mu, So even if I give the credit card to all these students, the average outstanding balance would be 1990. From where we have got this? From the sample I have got. Can't I say this 1990 will be the average, even if I go for the full-fledged implementation of this project? Can I say that? Yeah, yes or no? You can respond. Right. So no. Exactly. So because the population mean is different than the sample mean, so that's right. See, so this is actually again a sample, right? What if actually if I take one more sample, so would I get the same results? I might get a different results. I might get, let's say for example, 2500. So here, this is another sample. So if you take one more sample, I'll get different, the answer different sample mean, because the sample mean is a random variable. Remember yesterday's discussion, sample mean is a random variable. Based on that, you cannot take any business decisions. That means, so this is a sample mean is a random variable, and so this variable sample mean, a random variable, tend to give different answers, different values based on the situation, based on the data that we have sampled. Now, how to answer this situation? How to answer this question? That means, so I have the sample data, and I want to comment about this population data. That means I want to estimate, so the mean value, I want to estimate the mean value of this population. Okay, and I want to comment about this population. So how do you do that? Inferential statistics. I have sample, so apply inferential statistics on this data, then I'll so get the estimate of the population parameter. So that is what the inferential statistics that we discussed so far. Right? So that means using this data, using the sample, we are going to apply so inferential statistics, that is confidence intervals, we are going to apply on this data, and we are going to estimate the population mean range. So what would be the range of the population mean that lies so for this credit card full-fledged implementation of the card for the students. Right, so the interval estimate. So the interval estimate, that means, so we are going to estimate a range of values. Okay, so the range of values, so within this range of values, the population parameter mu would lie. Okay, so anywhere between these values, right? So this interval estimate, so how do we come up with this interval estimate? Equal to point estimate plus or minus margin of error. So that we are going to estimate using this formula. So this is the formula we are going to use for the confidence intervals. Let me write it if it is not visible for you guys. X bar, okay, plus or minus Z 1 minus alpha, okay, sigma by root n. Okay. So this is the formula we'll use. What are these terms? Let us understand. So X bar, as we know, X bar is nothing but average. The sample average, whatever we have computed, that is 1990 from the data, sample data. Sigma is a population standard deviation. Okay, so that has been given in the problem. N is a sample size, total number of data points. So how many data points we have in this data set? Our sample size 140. 140 students we have sampled, right? Right. Z is Z value. Okay, Z value, and 1 minus alpha. Okay, Z value. So we know how to compute in one of the sessions we have seen how to compute the Z value, that is so X, okay, minus mu by sigma, right? So X bar minus mu by sigma, that is how actually we can compute the Z value. Then you see 1 minus alpha. What is this 1 minus alpha? 1 minus alpha is called as confidence level. Confidence level. So how do you get this value? So this generally so will be at 95% or 99% or 90%. Right. So this information has been given to us in the problem statement, and this also, so we know, so they're asking us to choose one of these levels, confidence levels, we'll discuss if you take 95% what happens, and 99% what happens, 90% what happens. We'll discuss that. And what we do not know, so z we do not know, so we'll discuss how do we get this z value. And all we have to do is just plug these values into this equation, x bar plus or minus z into sigma by root n. Out of this, so this x bar is called as point estimate. Point estimate means the average of the sample data is called as point estimate, and this one so is called as margin of error. That means in estimating the interval for the population, how much error we are committing. That is what the margin of error. And the z is what is the probability that we are committing so this error. So that is the margin of error. So that gives us the interval width. Okay. All right. So as we discussed, x bar, okay, plus or minus z into sigma by root n. So when you say plus or minus, here we have two terms. One is with minus, the other one with plus. X minus z into sigma by root n. So x bar plus sigma by root n. Right. So these are the two values we'll get it. So x bar, what is x bar here? So 1990 that has been given in the problem statement, minus z. So z for 95% confidence level. So that z value we can get from standard tables. These are called as standard, okay, tables for z. Standard table, and any statistical book. So in the appendix, we'll have these tables. So these are the fixed values, standard values. Or you can also Google from the Google it in Chrome, saying that Z tables. So you'll get these tables. Okay. Or in Python, we can run this command to get this value. Right. So for 95%, so 1.960 is the value. Okay. So 1.960. So can someone please compute for me this one into sigma by root n already. So we have computed 2500 by square root of 140, that is 211. So this is with minus. So 1990 minus 1.960 into 211. Right? So then we have one more term with plus. So x bar plus 1990 plus, so 1.960, okay, into 211. Can someone please compute this? You can use Excel sheet or calculator. Yeah. Yeah, do not think that others would compute. So everyone is thinking the same, like others would compute. Please compute. Great. Thank you very much. So 1577 2403. Okay, I'll wait for one more answer just to confirm. So 1577 2403. Okay. Right. So this is a lower interval and this is upper interval. Upper interval. Fantastic. Thank you. So, right. So one more favor. So please compute for 90% interval as well. So in place of 1.960, just take 1.645. So just this we need for an example. So just replace this 1.960 with 1.645. So here as well as here, just compute that. So this is 1577 and this 2403. Right. Yeah, please compute for 90% confidence intervals. Right. So 1643, 2337. Fantastic. Thank you. Now we have got the value here for 90% confidence or 95% confidence interval. How much is the value? So 1577, 2403. Okay. So this is my confidence intervals for 95% confidence level. And when you say 90% confidence interval, so we have got how much it is. So 1642. Yeah. So 1642 to 2337. Right. So this is the interval that we have got 90%. Now let us see. So how do we understand these intervals? Right. Now, if I roll out this credit card to all these 100,000 students, okay, if they start using this credit card, and if you collect the average outstanding balances, student 1, student 2, student 3, that like that. So their average outstanding balance for all these 100,000 students so would lie anywhere between these two values with 95% confidence level. That means, so we have estimated the population parameter range using a sample statistics. So how we have done this? So we have a population data here. So we have taken a sample, that is 140 students data we have taken, and on this sample we have applied this descriptive statistics. That is, we have computed x bar, we have computed the standard deviation using this. So we have applied something called as a confidence intervals, which is inferential statistics, and using this we have estimated what is the population parameter range using this inferential statistics, that is confidence interval. So that means if you roll out this offer or project to all the students, their average outstanding balance so would be between these two values with 95% confidence level. Okay. With 90% confidence level, so the average balance would be between these two. Yeah, so these two values 1642 to 2337. Now, so if you see this number 95%, so if for the university, the minimum number 1577 is feasible for them from the business point of view. So they can go ahead and launch this project for all the students, because if they can get profits with this number, okay. So because we are saying that the population parameter can be anywhere, it could be 1577 or it could be 1578, like that, anywhere between these two numbers. For the university, okay, if this number is fine for them, they can go ahead and launch this program for the all the students. So that's how we can understand. Now, coming to the question, so which one we should go for? Should we go for 90% or 95%? Or why we are stopping at 95%? Can't we go for 99%? If I go for 99% confidence, that means the more the probability you can think of, okay, more belief if you go for 99%. So let us understand. So what is the implications that we'll get if you go for 99% and 90% or 95%? For example, so you want to play outside and you're checking weather forecast. If at all weather forecast tomorrow is somewhere around 30 to 32 degrees, then you want to go out and play cricket or football or the volleyball, badminton, something. And so that is for tomorrow's plan. Today you are checking the weather forecast. The news reporter is reading like this. Hey, tomorrow's temperature would be 0, or let's say for example 32 degrees with zero confidence. Okay. So this number is going to be useful for you. So if you read this, the news reporter said that hey, tomorrow's temperature would be 32 degrees with zero probability. zero likelihood. Would you believe this number? Yes or no? No, we don't believe, because even those guys, they themselves do not have any confidence on this number, right? So that's where actually they said 0% probability. Let us say, for example, one more thing. So with 100% probability, tomorrow's temperature would be, okay, between minus 150 degrees, okay, minus 150 degrees to plus 150 degrees with 100% probability. The 100% probability. Okay. Now to take the decision, so whether to play tomorrow or not outside, so will this information useful for you? Because we have 100% confidence on this number. No, because everyone knows, right? Everyone knows that tomorrow's temperature would be definitely minus 150 to 1 plus 150. Further, do we have to go for the news reporter? Even if you give me 100% confidence, so this everyone knows that will be between minus 150 to plus 150. But what I need is, I need a concise interval, because here the interval width is too large. A wide interval width, minus 150 plus 150, I can't take the decision because a lot of uncertainty is involved in this between 150 to plus 150. Even if you give me precisely on one number 32 degrees, but what is the confidence? Confidence is zero confidence. Here also I can't use this number. What I need a precise, concise interval with a decent level of confidence. Let us say, for example, if I give you, hey, tomorrow's temperature would be between, okay, so 28 degrees to 32 degrees, okay, with confidence of, so 95%. Now tell me, will this be useful for you or not? This is useful for us. So that is the reason, that is the reason, if you increase the, if you need more confidence level, your interval width would be more wider. When the interval width would be more wider, this will not be useful for us to take the decisions, business decisions. A lot of uncertainty is there. Okay. I want to reduce the uncertainty. So how can I reduce the uncertainty? How can I reduce the width of this interval? Just work on this confidence level. Decrease this confidence level to 95%, then the interval width will be decreased. And that is the reason. So do not go for 99%, 99.5 or 99.9%. If you go for this, yes, of course, there is a trade-off. Though you are getting more confidence, but you are going to lose in terms of width of the interval. And if you want to have more precise, more and more precise, so then again, definitely, when you say precise, only one number you want to have the estimation, only one number I need, then the confidence level would be zero or going to be decreased like anything. Okay. Let me put this in proper format. So I have 32 degrees. Or let me put this, the same example, 19. So 90. Okay. This is with 0. What is this 1990? The sample average, that is X bar. So if I launch the credit card with 100,000 students, the sample value, that is sample average value 1990, the likelihood is 0. Okay. Now, so if I go for 90, so I have got some 1640 or some value. Okay, let me go back. So what was the value that we have got here? 2337, 1643 to 2337. Okay, with so 90%. So this is very concise, but the confidence is not sufficient for me. I want to increase the confidence on this number. What we can do? Go for 95. So when you go for 95, the interval width would be increased definitely, because you want to have the higher confidence. So this is 95%. So here 1576. So you can see the difference between these two numbers, guys. So 1576 and 2403. So if I want to go for higher the interval 99%, then interval width will be increased further. That means, so as you discussed, so in the temperature example, if you want to have exactly one value, so like 1990, then the confidence on this number is a 0. That means, so if you roll out this project to 100,000 students, so what is the average outstanding balance maintained by those guys? So if you say that, hey, that would be $1990, that is with zero likelihood, 0% likelihood. Okay, right. I want to increase this likelihood. Then we can use our formula x bar plus or minus. Okay, so z into sigma by root n. So this is where actually we'll use the interval to come up with an interval here. So this is a range of your population parameter would lie here with a reasonable amount of confidence, that is 90%. So this 90% is not enough for me. I want to increase more, but with the cost of increase the width of this interval. So when I go for 95%, definitely it will be increased 1576 to 2403. Yes. So if this is fine for me, 95% is a decent and reasonable amount of the confidence I can have on this number, then I can go for this. Then how do you represent? If you roll out this, the project, the population parameter would lie within this range 1576 to 2403. Okay. And if you want to increase more and more, yes, so that would increase, the width would be increased. Okay. So that's how actually we can understand this confidence intervals. All right. Now, let us understand a little more in deeper. How do we interpret? How to interpret this 90%? What do you mean by 90% exactly? Is this a probability? Is this a chance or likelihood? Let us understand what do you mean by 95% confidence intervals. Right. So let's assume that we have this 100,000 students. Okay. The same problem. So we have taken a sample. This is sample 1. So this sample 1, so we have constructed a confidence interval. So let's say we have constructed a confidence interval, the first confidence interval. So before that, so let me give a number. Let us say, for example, 2100. Okay, what is this 2100? So this 2100 is, so if you roll out this project to all the students, 100,000 students, their average outstanding balance is 2100. That means this is a population mean. Just assume that we got to know this number. Just assume that we know already this number. Just pretend that we know this number 2100. Okay, that is the population parameter. Now I've taken one sample. So I have estimated the confidence intervals, so which is 95% confidence interval. So the 95% confidence interval, let's say for example is this. The first interval is, so this one is 1600, then 2200. Then again I have taken one more sample, let us say. Okay, I have taken one more sample. So this is sample 2. So with this I have constructed one more interval. So this interval is like this. So this is 1500. So 2150. So I've taken one more sample. Let us say, for example, S3. So S3, when I construct this confidence interval, so the values are like this. So the minimum value is 2200. The upper limit is 2600. So like that, so I have taken multiple samples, like 100 samples. Yes, 100. So with all of these, the samples, I have constructed this multiple confidence intervals. The fourth one, fifth, sixth, like that. So this is, let's say, 80th one. So 80th one is like this. 1700. This is 2300. So further, I have constructed the 100th one. The 100th one, let's say, for example, so this is, so 1500, and let us say this is 1900. No. So the motive behind this exercise is just to let you know that, so which interval contains the true population mean. What's the true population mean? So this 2100. So we discussed, right? Just pretend this value is a population parameter. That means if you roll out this offer to all the students, so this would be the average balance would be maintained by, so 100,000 students. Now I want to check, so which interval would contain this value. Because see, all this exercise, why we are first of all constructing these confidence intervals? To construct this, the objective of this confidence interval is to capture in which range this population parameter would lie. Whether this is a range, or this is a range, or this is a range. So that is what we are trying to do. Now, so the first one, do we have the population parameter, so in this range? Please answer your question. Answer the question. So do we have the population parameter in that range, guys? Yes or no? Yes. So we have population parameter in that range, exactly. And second one, second one also yes. That means, so the 2100 will be there in this range. That means, so this interval has the population parameter. Great. And what about third one? No. So this missed. Okay. So this interval has missed the population parameter. And again, 80th one, we have, 100th one, we don't have. That means there are a few intervals, confidence intervals, that would miss to capture the population parameter. So how to estimate how many number of intervals would miss the population parameter? So that is what actually this 95% means. 95% confidence interval means, if you construct 100 intervals, 100 confidence intervals like this by taking multiple samples from the population, out of this 95 of these intervals would contain true population mean, and 5 of these intervals would miss like this, Okay? So that is what the 95% confidence interval means. Let's say, for example, 90%. If I say 90% confidence interval, how do you interpret this? If you construct 100 confidence intervals, 90 of such intervals would contain the true population mean like this. The other 10 would miss the true population mean. Why? So if you say 90%, yeah, 90%, the interval width would be very, very concise. That means, so this would be here, for example. Okay, so this would be here. Okay, so this would be here and this would be here. That means because of the low interval width, there is a more chance that that interval would miss the the true population mean. If I say, so 99% confidence interval. So when you say 99%, the interval width will be increased. That's what we have seen in the previously, right? And this width will be increased. That means the interval range would be increased, and there is a chance that, so the true population mean, most of the intervals would fall into that. Okay, so that's how we can understand. So the true interpretation of the confidence intervals. So it is not a probability, it is not a likelihood. So this is, if you construct 100 intervals, so based on your level of confidence, at least those many intervals, so would contain the true population mean. Okay, so that's how we can understand this confidence intervals. All right. Right. That is the question. Then why we have to take the 99%? No, we will not take 99%, just to check how the things are. Okay. So when you go for the real implementation of these confidence intervals, so generally we will take at 90% or 95%. Okay, 90 or 95% are so good to go with. Okay, now let us go back to this problem statement here. So if you read this problem statement, so and also if you see our formula x bar plus or minus z sigma by root n. Okay. So what did we say about the sigma? Sigma is population parameter, right? So population parameter. And in this case, so in the problem statement, they're asking us to assume that the population standard deviation is 2500. So this is not from the descriptive statistics. So they are asking us to assume. But is it possible to get this population parameter, the population standard deviation? So when you are working on this on a real-time problems, no. So this we will not get, because the population parameters will not get a chance to use, or will not get a chance to compute them, right? So in that case, how do we compute this, the confidence intervals? So this sigma we cannot use because the population parameter we will not get. So when you are working on a real life situations, so in that case, so instead of using the standard normal distribution, we would use something called as t distribution. So t distribution is a continuous distribution. Okay, and our formula would transform to right. So this is when you know the population parameter, that is standard deviation, population standard deviation. But generally we do not know this unless you are working on a predefined problems or theoretical problems. So when I have to work on the real life problems, I have to use this formula. What is this formula? So this formula uses t distribution, and in place of the population standard deviation, we would use sample standard deviation. So this formula, let me rewrite here. If you're not able to see this properly, x bar plus or minus t into 1 minus alpha comma n minus 1 into s by root n. S by root n, right? So this is a formula. So from Z standard normal distribution to T distribution, so it would get transformed. So then everything is same, just we have to compute for this T value. So T again will have the standard tables that are available. And yes, we know already from this problem statement, N we know, then compute and we'll get to know the confidence intervals, right? Yeah. Now there is a comparison between this standard normal distribution with the T distribution. Let me go back to the earlier, the previous slide. Right. So there is a comparison between the T distribution, is also called as students T distribution. This curve is a standard normal distribution. So that we discussed as part of our continuous distributions. And you see this below, this curve is students T distribution. And when we have DF, degrees of freedom, is nothing but DF is equal to N minus 1. Number of data points minus 1 is called as DF. So that is degrees of freedom. Yeah, degrees of freedom. So when DF is equal to 1, so there is a difference between the standard normal distribution and the T distribution. As the number of data points increases, so the differences between the standard normal distribution and the T distribution reduces. You can see the gap. And as DF becomes 10, so it started to converge with the standard normal distribution, the T distribution. When DF equal to 30, it is almost so on the lines of the normal distribution or standard normal distribution. The general notation is as n tends to infinite, as there are many number of data points, my T distribution tends to standard normal distribution. So this notation is basically refers to the standard normal distribution. Okay. So n0 means 0 mean, and standard deviation is 1, or variance can say. So this is mean and this is variance. This is standard notation for the normal distribution, right? So my T distribution would converges to the standard normal distribution as number of data points in the data set are infinite. Okay, so that's how. So there is a small difference between this t distribution and n distribution or a normal distribution when you have huge number of data points. Right. Now with this, if you compute the credit card balance example, so we have 1 minus alpha, that is 95% confidence level, n is total number of data points are 140. The t value for 95%, so t is characterized by degrees of freedom. That means for each of this df value will have a different t values. So that is what the t distribution is characterized by degrees of freedom. For 95% confidence level and df is n minus 1, that is 140 minus 1, 139. So here you can see, so 0.95 comma 139 is equal to 1.98. So how do you get this? So use this command to get this value, or you can also search for the t tables. Just you can search in the Google t tables. You will get this value 1.98 and plug this value into the equation, that is, so x bar plus or minus t 1 minus alpha, okay, n minus 1 degrees of freedom, so s by root n. So x bar we know already 1990, okay, minus t value 1.98, s by root n we have 239. So the other one is 1990 plus same value 1.98, 239. Okay, so this value is this, right? So 15, 16 and 2464. Now let us compare the values that we have got from the t distribution as well as the values that we have got from the standard normal distribution. So if I recall, for the same 95%, the confidence level, so we have got 1577, 2403. Okay, so this is what actually we have got from Z distribution of 95%. This is from Z. And if you see this 1516 and 2464. So this is with t distribution for same 95% interval. And if you compare these two, so here you can see that there is a width increased. The wide width is there. So when you use t distribution, the interval width is more in comparison to z distribution. So this is because the t value is more here in comparison to z value that was 1.96. That is one reason. The other reason is, you see this value here. So if you see the formula, so x bar plus t into, so s by root n plus or minus. So this width would be defined. So how deviates this value from the mean value? So the s is directly contributing to the deviation. So if this value is more, then we are going to get huge width. If this value is low, then we are going to get low width. So earlier we had 2500. Now it is 2833. So because of the difference in these numbers, that is the population standard deviation and the sample standard deviation. So because of that, you can see the wide width for the t distribution, right? So remember one thing, whenever you get a parameter from the population, so definitely you would get a finer width, a concise width. And we are not using in this the population parameter value. Here we are using sample standard deviation. So definitely we'll get the wider width. But so we have to go with this only. We don't have any other choice for this. Okay. So that's how we can compute the confidence intervals for a given problem. Okay. All right. Yeah. All right. Now let us find the confidence intervals for the examples that we discussed yesterday, the stock prices for BEML and Glaxo gains, Okay, so we computed yesterday the gains, right? The gains from the BML as well as the Glaxo. Let us compute confidence intervals for these two gains. Right, so load these libraries and Glaxo, the data frame we have loaded. Let me show you this data set. Right, so these are data set, and we are going to compute the confidence intervals for these gains. So what does it mean? So we have taken sample. That means we have taken a data from 2010 to 2016. Okay. Now we are going to compute the confidence interval. Meaning, if you take whole data of this company, okay, and if you compute the gains would be between the confidence intervals that we are going to compute. Okay. And the command for that is stats.norm interval. So this is direct command. You don't have to manually compute that. So whatever we have done is that is a manual way of computing to understand what is going behind the formulas. Right? And this is a direct command that we have stats.norm interval. 0.95 is a 95% confidence level. And we have to give the mean value of this data set as well as standard deviation of this data set. Right? So the interval is this. Minus, okay, 0.0258 to 0.0266. That means if you take the entire company data and if you compute that gain for this column and that gain and average of that gain, so would lie within this range. Okay, that means so the negative value indicates the loss, the positive value indicates the gains. Okay, so that means 2%, 2.5% loss and 2.6% gains. So always it will be between these two values. Okay, so that's how we can compute this for a real life situation. Now let us compute for BML as well. Right, so this is minus 0.51 till plus 0.052, that is minus 5% to plus 5%. So BML, as we discussed yesterday, is a highly risk volatile stock, and that's what actually you can see here. So if you take all the company data, compute the gains, and then if you want to see the average of that gain would lie between these two values. Okay? So that's how we can apply for a real life problem. All right. Okay, so that is the story of confidence intervals. Let us take a break now, a 5 minutes break. Then after that, we are going to discuss about the hypothesis testing. So which is the last, the inferential statistics. Then we'll move on to the data mining concepts. Yeah. So the code is pretty simple. Just put the required libraries. Okay, then give how much the confidence level that you need, and give the mean value of the gains, the data set, as well as standard deviation, then execute it. The similar way for BML also. Okay. All right. So let us take a break now, a 5 minutes break. Yeah, hello all, welcome back. Okay, so now let us discuss about the hypothesis testing. Right. So hypothesis is also one of the inferential statistical tests. Okay. So like the confidence intervals, and let us understand. So what is the purpose of this hypothesis testing, and where do we use? Let me give you a hypothetical scenario, an example here. Let's say, for example, there are two companies, uh, two pharmaceutical companies. So company A, okay, and company B. So these two companies are producing tablet, a medicine, so that relieves headache. Okay. Now, so the company B has claimed that, hey, my headache reliever tablet will have more effect than company A's tablet. Meaning, if company A's tablet would take 5 minutes to give the relief, my tablet so would give you the relief within 2 minutes only. That means my tablet is more efficient than company's A's tablet. So this is the claim that company has done. Now, how do we verify this claim? So how do you test this? So just company B has claimed, and so should we go ahead with that? No, right? So there should be some procedure to test this claim in a general way. So in a brute force method, as we discussed last time also. So how do you test this claim? So we can test like this. For example, question here. Right. Okay. Yeah. So how do we test this claim? What we can do is we can give this tablet A to all the population. All the population means all the people who are living on this earth who gets headache. That means person one. Okay, I'll write it here. Yeah, I'll give person one. Give the tablet to person one, and just measure how much time this person one has got relief. Let us say that is 4 minutes. Person two. Okay, 3 minutes. Person 3, so 1 minute. Person 4, 5 minutes. So like that, all the people who are living on this earth, all 7.5 billion people, you give it to them and record all the details. Okay, and then take the average. Let us say the average value came out to be for example 3.5 minutes. So in 3, on an average, in 3.5 minutes, so they are getting relief. And similarly, give the tablet B also all 7.5 billion people, okay, on this earth. The first person, when you give the tablet B, so that guy has got relief from the headache in the within the 1 minute. So this guy 4 minutes. So third guy, let's say 2 minutes. So this guy 6 minutes. So like that, we have the minutes. When you take the average, so this average is, let's say for example, so 2.5 minutes. Okay. So what can we say about this now? So can we say the tablet B and medicine B is more effective? Yes, of course, because we have tested on the population, whole population we have tested. So this claim, and so we can see the numbers within 2.5 minutes. The tablet B, the medicine B, is relieving the headache. Tablet A is taking 3.5 minutes, which is more than this. So this is, we have tested on the population. But is this a viable option? Practically, is it possible? No. So companies, so if they have to produce all these 7.5 billion tablets, then they'll have to just close the company. Right? So because of these practical situations, we cannot go with this kind of procedure. Then what else can be done? So what do we do? Right. So what we can do is, so I can take the sample again. So take the sample from this data and give A and B two tablets. take the sample from this. Okay, so give tablet A and tablet B. So first person, the values are, let's say, 2.1 minute, okay, second person 5 minutes, third person 4 minutes, like that. So give to the sample people and take the average. So this average is 3.9 minutes, and this one, the same procedure you have to follow for this also, 5 minutes, 3 minutes, 1 minute, 2 minutes, like that. And this average, let's say, so 3.7 minutes. Yeah, so these are the values that we have got on this sample. Now, can you tell me, based on this data, so which company's medicine is more effective? Company A is more effective, company B is more effective. Okay, so should we should we announce that company B is more effective so than company A? So just check what we are trying to do here. So this 3.9, 3.7, what is that average? It's just a sample average, guys. So based on the sample averages, can we take the decisions? No, because sample mean is a random variable, right? Because if I take one more sample, for example, so we may not give any guarantee that the same results would be repeated, right? So if I take one more sample, so I might get the A average, for example, so 2 minutes, okay, B average, so I might get, let's say, so 3.5 minutes. So this is possible. If I change the sample, I'll get the different values because this is sample. Sample mean is a random variable. The based on this sample means you cannot take the decisions. Then how do you take the decisions? Hypothesis testing. Okay. What we do is, so take a sample. So just compute the descriptive statistics, apply this hypothesis testing on the data. Then we will comment about the population. So which one is more effective, whether these two are equal or not equal, right? So that is where we'll apply this hypothesis testing. And also one more, so one more application. So I want to compare the temperatures of two cities. Temperatures of two cities, city 1 and city 2. Okay. Whether the temperatures of these two cities are equal or is there any difference between these two temperatures, cities temperatures. So what I can do, I can collect the data throughout the 1 year. I can collect the data throughout the 1 year. So whatever the averages that I get here, okay, averages and this average, then I'll compare these two using this hypothesis test. Then I can comment about the overall temperature between these two cities. So based on these averages, you cannot comment. You cannot say that, hey, so the city 1 temperature is more than city 2 temperature. Probably you can get some idea. Okay, some idea you will get, but so based on this, you cannot take the business decision. You cannot conclude the things. So that is what the random variable is sample mean is. So that means if you want to compare the two quantities statistically, then we'll go for the hypothesis testing. Okay. Right. So here another example. I have two processes. Let us say process A and process B. Okay. And these are the efficiencies of the processes. That means you can think of productivity levels of a department A and department B. Now I want to comment about whether which department has more productivity levels. So these have been computed. So by taking at various months, let's say this has been taken from month of Jan. Okay, this is Feb. Okay, this is Feb. Okay, March. So like that for various months I've taken. And I want to check whether which department has highest productivity levels. So if you see these numbers, so it is difficult for us to say that, okay, which department has highest, more the productivity levels. So generally what we do, go for descriptive statistics, that is mean. Okay, mean, and compute standard deviation as well. Now let us do that now. So the process A, or you can think of this as a department A, and total number of data points are 10, 10, mean values are 84.24 and 85.54. And standard deviations for department A 2.90 and 3.65. Now, can you tell me which department so has more the productivity levels, A or B? Yeah, answers guys, A or B. A, B. Okay. So you don't want to get which one has higher productivity levels. A. Is this sample mean? Of course, this is sample mean. Yes. B, A. Okay. So the right question is, yes, is this sample mean? Yes, this is sample mean. And again, based on sample means, can you take the decisions? Can you conclude? No, right? So that means, so this also based on the descriptive statistics, based on the date, the mean, sample mean. So you cannot compute or you cannot conclude that which department has highest productivity levels. But at high level, probably you could say that, okay, 85 is more than the department A, probably you can say that. Okay. But again, so you can see the standard deviation here. The consistency is not that much. That means more fluctuations are there in the data. Right? Yeah. So based on this descriptive statistics, so at high level, you can say that 85.54 is more than the 84.24. So probably we can go for that. But if you want to take any business decisions based on this sample mean, is strictly no. So for this, again, we'll conduct the hypothesis test between these two departments based on these two values, and we'll conclude, hey, whether these two are equal or not equal, which one is more, which one is less. Right. So now let us understand. So how do we compute this hypothesis test? Okay, let me have a slide here. Now we are going to discuss about the procedure to conduct this hypothesis test. Okay. So conducting this hypothesis test is a step-by-step process. Let me write it down one by one. The first one is define hypothesis. The first step is define hypothesis. Okay, what is that? Defining hypothesis. So as part of definition of the hypothesis test, so we have to identify two terms. One is null hypothesis, okay, or H naught. So this would be denoted as H naught. The second one is alternate hypothesis. So this is HA. What are these two terms? Let us go back to our earlier example where we want to test the two medicines A and B, whether these two are equal or not equal, right? Now we will assign the few statements to these two definitions, null hypothesis and alternate hypothesis. So we will assign to this null hypothesis means of whatever we have collected, the means of the relief time. So we have taken the sample, right? We have taken the sample and we have given the tablet A to the people and we have collected the relief time. The mean of relief time from the problem, the tablet A, is equal to the mean of the relief time when we have given the tablet B. That means both are equal. There is no difference. See, company B has claimed that, hey, my tablet is more efficient than tablet A. The null hypothesis says that, hey, your company tablet is not efficient. Both are equal. There is no improvement at all. There is no change at all, first of all. Okay, you both are equal. So that is what the null hypothesis says. And the alternate hypothesis, what it says is you both are not equal, guys. Okay, not equal. Mu A is not equal to mu B. That means company A and company B are two different. They are not equal. There is a definitely there is a difference between the tablets. Remember, null hypothesis always, yeah. So null hypothesis always says that status quo is being maintained. That means there is no change at all. There is no improvement at all. Everything is as usual. Whatever the situation was there in the past, the same situation so is going to be continued in the future also. And also, the null hypothesis is dead against taking any action. Okay? It says that hey, do not take any action. Nothing is going to be changed. Just sit back and relax. Do not take any action because nothing has changed. Everything is same. So that is what the null hypothesis says always. So when you are formulating this null hypothesis, always you have to look for these kind of statements and you have to assign. So this kind of equal to not equal to this null hypothesis. Always it says that both quantities are equal. If I say that a temperatures of two cities are equal or not equal, so null hypothesis always says that these two cities temperatures are equal. City 1 is equal to city 2. Right? And coming to alternate hypothesis, so this the alternate hypothesis HA so always encourages to take the actions, take the action. So we would see the improvements. Two things are not same, like mu A is not equal to mu B because there is some change, some improvement has happened. So that is what alternate hypothesis says. Okay, then these two are exactly opposite, exactly opposite. So if null hypothesis says that mu A is equal to mu B, so HA says mu A is not equal to mu B. So like wife and husband, right? So then the second step. So find the suitable test to be conducted. Find the test to be conducted. So broadly, we are going to discuss about two tests. One is Z test and T test. Z and T test. So when you go for Z test, we'll go for Z test when we know the population standard deviation sigma and the number of data points are more than or equal to 30. Then I'll go for the Z test. So how do we compute the Z test? The Z value is so X bar minus mu by so S by sigma by root n. This is sigma by root n. So this is how we will compute the Z value. And coming to T test. So T test will compute. So when we do not know the population standard deviation, then I'll go for T test. So how do you compute T value? So T value X bar minus mu by S by square root of n. So this is the formula I'll use to compute the T test. Right. So once I compute the T value and Z value, so then the third step is compute the probabilities. So probability, okay, for T value. Okay, whatever the value that I get. Okay, this X bar is nothing but the sample mean. Mu value is this mu, and S is sample standard deviation, and N is total number of data points. Then I'll get a numerical here. So the numerical number like 1.2, 2.3. So these are the numbers I'll get here. Okay. For this, I have to compute the probabilities. How do we compute the probabilities? So we know how to compute the probabilities as per our normal discussion, normal distribution we discussed, right? So this is my mean value 0. When you say 1.2, I can mark 1.2 here. Then I can compute the area, right? So area to the left side or right side, that is the compute the probability for T value. So this is called as P value. Now, what are the P value that you get here out of the step 3? So this is called as P value. Then fourth step is, so we have something called as alpha. Okay, alpha. So get the alpha from the management. Get alpha value from management. So what is alpha value? Yes, we'll discuss that. So generally alpha value would be 0.05. This is the standard value in the industry. The fifth step is compare the p value that you have got as part of step 3 with alpha value. Okay? So compare p with alpha. So if p is less than, this probability value is less than this alpha value, then I'll reject null hypothesis, reject H naught. So what do you mean by rejecting H naught? So rejecting H naught means, so I'm going to reject this statement. So what is that statement? Both are equal. Both tablets are equal. So this statement would be rejected. And I'll go with this statement. That means, yes, both are not equal. And based on the mean value, so if at all which mean value is more, then I'll conclude that here tablet B is more efficient than tablet A. Right? So that's how we will conduct this hypothesis test and we'll apply to the data set and we'll conclude. So in the population, whether these two are equal or not equal, and based on this, whether we reject the null hypothesis or we fail to reject null hypothesis, we'll take a decision on that. All right. Right. Now, so now let us discuss about one problem statement and let us understand all these steps. So we are going to compute all these steps with that example. Let me. Yeah. A supermarket loyalty program. Okay. So a supermarket plans to launch a loyalty program. So if it results in an average spending per shopper more than $120 per week. Okay, so let me explain this to you. There is supermarket. So they want to increase their business as part of their business plans. So they came up with a new loyalty program, kind of a discount program. Okay, a discount scheme or discount program, like 1+1 offer, 2+1 offer kind of thing. Now, if they have to give this 1+1 offer, okay, so the customers have to purchase more amount. They have to come more number of times and they have to purchase more, then only, so this scheme they can run. Otherwise, so this scheme would be run into losses. So for that, so they have a business plan. So as per the business plan, there is a threshold value. So this program would be successful only if the average spending per shopper is more than $120 per week. Then we can say this loyalty program is successful. So if at all the customers who enroll for this program, and if they don't spend, so average of more than $120 per week, then this would run into losses because they are giving some offer, 1+1 offer. So if more number of people would buy, so then this program would be successful. If 1 or 2 people would buy, so then they have to additionally give 1+1 for the same price. Then, so that is a loss making for the supermarket. Okay, so this is the hypothesis they had. Now, so to test the waters again, as in the case of the credit card, so here also the supermarket has launched a market study. So that market study is this. So 80 shoppers have been enrolled for this pilot program. And these 80 shoppers, this is my, let's say for example, population data. Okay. From this population data, I've taken the sample. This sample is 80 people. Okay. And so these 80 people have enrolled for this program. And these people are started shopping. And I've got the details. First shopper. So how much this guy has done? Let us say in a week, $120. Second shopper, okay, second customer. So this customer has done $100. So third customer. So this guy has done, let's say, $150. So like that, so all 80 people have purchased within a week. And when you take the average of this value, so that came out to be $130. $130, the standard deviation of $40. Now the question here is, should the loyalty program be launched for all the population data, for all the customers? So that is the question that we want to answer, right? Now, so can I say that, so even if I launch this loyalty program 1+1 offer to all the customers, can't I say that the average, the balance per shopper per week would be $120? Or so this is 130 for sample here I have got. So can't I say that this average balance per shopper per week would be $130? Why can't I say that? And based on this, I can say that go ahead and launch this loyalty program. Can we say that? Yes or no? No, exactly, right? Because random variable, fantastic. It's the only sample data, absolutely correct. The sample mean is a random variable. This is only the sample data. If I take another 80 people data, so we don't get any guarantee that I'll get the same value. I might get different value, right? So that is the reason will not depend on this sample means. Now here I'll go for the hypothesis test. Right. Now let us conduct. Yeah, let us apply all these steps, whatever step that we have discussed. Excuse me. Right. Let us write down all the data that has been given to us. So n is 80. So the sample average, sample mean is $130. Sample standard deviation, that is small s, is $40. Then, so this $120 would be considered as population. Okay. Because if in the population, if it results more than $120, then I can go for this loyalty program. Right. The first step, define the hypothesis, null hypothesis and alternative hypothesis. Okay, as we discussed, the null hypothesis always discourages you from taking any action. It says that, hey, there will not be any improvements even if you launch this program. If you say that there will not be any improvement, that means, so even if you launch this program, that would be a utter flop. You will not get any profits. So that is what the null hypothesis says that. So that means if you launch this program, if you launch it to the population data, so definitely that would be less than $120 per week per shopper. So when the population value, if you launch it to the population, if that value is less than $120 per week per shopper, then we don't launch it because this would be a loss making project. Then on the other hand, HA says that, hey, you have to launch it because so it would be more than $120 per week per shopper. Why? From where we have got this 120? From the business threshold value. The business says that if it is more than 120, then this program would be successful because they have all the calculations based on the profit and loss analysis. And that is the first one. The second point is, find out which test to be conducted. Okay, T test or Z test. Now let us evaluate. Z test will conduct when we have the population parameter sigma, but here we have not been given any population parameter. That means we are not going to conduct this. We'll conduct T test. T test, how do you compute? X bar minus mu by S by root n. So that is equal to X bar minus mu. So 130 minus 120, that is 10 by S by root n. S is 40. Okay, 40 by square root of 80 approximately. Let us go for 9. So 130 minus 120, yes, X bar 40 by, yes, that is right. So that is, so 9 by 4. Okay, so these approximately, so 2.2. Okay? So these are T value that we have got. Then third step. So find the probability value for T. Yes, so what is the T? 2.2. Now we have to find out the value, the probability value to the right of 2.2. So this might 0 T distribution, and 2.2 I can mark here somewhere 2.2. Now we have to find out this area. this area. So how much is the area? So this we have to find out, and we have to use so this command to find out that area. Okay, and this area approximately, let us say for example 0.01. I'll compute that. I think that is answer is there in the next slide. Let me see this. How much is this? Yeah, 0.01. That's right. Right. So the value is 0.01, the p value. Right. Now fourth step. Okay. The alpha. So we have not been given alpha value, so we can assume that 0.05 alpha value. Compare. So p value. So p value is 0.01. Okay. Compare p with alpha. So since p is less than alpha, so 0.01 is less than 0.05. So as per our steps, so reject null hypothesis. Okay, reject H naught. That means, so we are going to reject this H naught. And what is the decision we are going to take? The decision we are going to take this. If you launch the loyalty program to the population data, all your customer base, so those guys are going to shop per week would be more than $120. Right? So that means we would conclude that go ahead and launch this program to the population, so that so definitely will increase your business. Okay, so that's how we can take the decisions based on the hypothesis test. Right. So that is the story of hypothesis test. How we can compute. Yeah. So how we can compute this hypothesis test. So with these problems, yeah. The example. Right. So any questions? So any clarifications needed? All right. Now let me show you. Yeah, let me show you how do we compute this in Python directly. So this is a manual way of So this is a manual way of conducting this hypothesis test. That means so just get the information and compute each step one by one, and then compute these p values and all those things. But every time are we going to do like this step by step? No, not necessarily. But we should have the good understanding of how the hypothesis test would be conducted. Right now, we are going to discuss about the automated way of conducting hypothesis test directly in Python. So let us understand that now. So before that, so let me give you the variation of the t-test. Right. So there's a question, can this be trusted in the medical diagnosis? Yes, based on the context, based on the value that we get, we can take a decision. Yes, this is being applied. In the clinical trials, this is being applied. So there are variations of the hypothesis testing. The first one is one sample t-test. Okay, one sample t-test. Let me write it, one sample. Then we have two sample. One tail, then two tail. So these are the different variations of t-test. What do you mean by this? The one sample is, so we'll have one sample data set. Okay. When you say sample means a data set. I have a sample data set, and the mean of this sample data set would be compared against a benchmark value. A benchmark value or a standard value. A standard value. The mean of this sample so would be compared. So the benchmark value or a standard value or a value given by the management. Then that is called as a one sample t-test. The two sample is we'll have two sample data sets. Two sample data sets. The means of these two samples would be compared. So we can say this sample is from the company A and this sample is from company B. The means like mu A is equal to mu B mu A is not equal to mu B. So this is, so what actually is called as two sample. You see here we have two sample, not need not be equal, it can also be greater than less than. Yeah, when you have the two data sets, so from the two different entities, or you want to compute or compare the temperatures of city 1 and city 2. That means you have to collect the data from the city 1, that is one sample, and collect the data from city 2, that is another sample. So that means I'll get the two sample data sets, compare the means of these two samples, that is called as two sample t-test. Then one tail. So one tail t-test is basically in the null hypothesis. If you see null and alternate hypothesis, the symbols like less than mu A, okay, less than mu B, mu A greater than mu B, right? Right. If you see less than or greater than, this indicates we are conducting one tail test. One tail test. So that means, so we are going to compute the probabilities, these related to probabilities. One tail. One tail means, so earlier we have computed the probability, right? So we have taken this tail probability, right? So that means, so we are going to compute the probabilities. So this tail or this tail. That is one tail t-test. Okay, so this or this probability will compare to find out the p-value. Okay? So that we can easily find out based on this what kind of symbols we are using in the null and alternate hypothesis. And coming to two-tail t-test, the two-tail t-test, we will have equal or not equal. Mu A is equal to mu B. Mu A is not equal to mu B. So in this case, we'll have to compute the probabilities in both tails. So this side and this side. Okay. So the final p-value would be, so just consider this a p1 and this p2. The final p-value would be p1 plus p2. Okay. This p-value we will compare with alpha again to take the decisions. Okay. So the main difference between one tail, two tail is, so based on the problem statement, we'll have to use these symbols less than, greater than, or equal to, not equal to. When you use equal to, not equal to, then you'll have to go for the probability values both sides. So this side as well as this side, because we want to find out the changes have happened both sides, right? And compute these both values and add it up, then that would be the final p-value, and compare this with the alpha. If p is less than alpha, again reject null hypothesis. And coming to one sample to two sample, yes, here we'll have only one sample data, and here we have two sample data sets, two data sets here. Right. Now coming to the problem that we have conducted. So what is that problem? Is it a one sample, two sample, one tail, two tail? The combinations are possible, guys. That means the problems could be one sample, two tail test, one sample, one tail test, two sample, one tail, two sample, two tail. The combinations are possible. Now the supermarket problem. So how many tails and how many samples? Okay, let me explain that. The supermarket problem. So we have collected the data, 80 people data, right? 80 people data. That means I have one data set, one sample. That means one sample data. So this mean, so the management has asked us to compare with $120. This is the standard value given by the management. So that indicates, so one sample test. Okay, so that is one sample. And how many tails? So have we computed one tail or two tail? So if you recall the symbols that we have computed this, that means mu A is less than or equal to 120, mu A is greater than 120. So when you use these symbols, so that indicates we have computed one tail t-test. So then that means, so we have computed or conducted one tail, one sample, one tail t-test. So that is important actually. So you have to write the test heading, what test you have conducted, one sample, one tail, or two sample, one tail. So the combinations. So based on the situation, you can go for this. All right. Yeah. All right. Yes, that's right. Okay. Right. So that's all for today. We will stop here. And tomorrow we'll see so how to conduct this hypothesis testing in Python directly. Okay, so then we'll start our the data mining topics. The linear regression will start tomorrow. Right. So the attendance link has been posted. So any questions? So we'll send you the codes and files. Okay, we'll let you know how to access those files, guys. Yeah. We'll let you know, guys, that. Okay. Yeah. So all right then. Yeah. Okay. So thanks for joining today, and we'll meet tomorrow, and we'll see the other topics. Thank you. Bye.